Hello everyone, I'm İpek Küçükkaya. I'm an undergraduate student at Bilkent University in the physics department. This presentation video is for my project in Physics 102. I will be showing you the footage of the experiment that I conducted in the physics lab. I will also explain the details of my experiment step by step, and I will show you the material that I use in my experiment. Before the experiment, I want to give some theoretical background. A solenoid is a long wire coiled into multiple loops that carries a direct current. Ampere's law is used to derive the magnetic field's formula for the solenoid in the experiment. The magnetic field outside the solenoid is so weak that it can be considered negligible compared to the magnetic field inside. Therefore, the first term in the sum can be considered as zero. Moreover, the magnetic field is perpendicular to the segments BC and DA in the solenoid. It is almost non-existent between and outside the wire loops, which reduces these terms to zero as well. Thus, the integral is simplified into the form b dot d's integral from c to d. Current inside is n times I. I is the current which passes through one loop. To observe the relationship between the current and the magnetic field, we rearrange this and solve the equation for B. This experiment is called analyzing the effect of currents and solenoid turns on the magnetic field strength inside the solenoid. The objective of this experiment is to analyze the relationship between the current, magnetic field, and the number of loops per unit length, which is also called the number of turns of a solenoid. I will also compare the theoretical and measured value of the magnetic permeability of free space. The number of turns for the solenoid I have chosen are 400 and 800 turns. The current values I chose start from 0.1 ampere and it goes up to 1 ampere with 0.1 ampere intervals. This interval is chosen to obtain consistent results and to reduce the errors obtained in the experiment. A ruler is used to measure the length of the solenoids. They are both 0.04 meters. I also used a Gauss meter, a power supply, and some cable sets. Also, for computational results, I used the program Tracker to plot the graphs. I used the camera of a phone to record each trial I conducted. Here, you can see the equipment that I used in my experiment. Now I want to talk about the procedure. I took the solenoid with 400 turns, I connected the cable sets to that solenoid, and I turned on the DC power supply. I connected one endpoint of the cable to the power supply and the other end to the solenoid. Using the knob of the power supply, I changed the resistance until there is 0.1 ampere current in my experimental setup. I increased the current by 0.1 ampere by changing the resistance with the knob of the power supply for each consecutive trial. Using the Gauss meter, I measured the magnetic field strength inside the solenoid. I did the same procedure for the other solenoid with 800 turns. Here are some of the videos that I recorded in my experiment. After calculating the magnetic field for each trial, I noted the values of the data points in my table as shown. I plotted graphs for current versus magnetic field strength. The graph is linear because current and magnetic field strength are proportional with each other. By using the equation for slope, I derived the magnetic permeability of free space and calculated it for both of the solenoids. The values are seen for both of the solenoids. The percentage error was calculated with the formula shown. For the solenoid with 400 turns, the percentage error calculated was 97.6%, and for the other solenoid with 800 turns, it's calculated as 98%. Unfortunately, these errors were greater than anticipated. Because the gap inside the Gauss meter is quite large, the probe may not have been placed in the same exact position in each trial. The errors might have been caused by human errors or the device itself. All in all, the experiment has been a great opportunity to observe the relationship between the magnetic field strength, current, and number of turns of the solenoid. Thank you for your attention.